Hi there. In this brief video, I'm going to show you how I've used principal component analysis as a method of dimensionality reduction with the college scorecard data. As I mentioned previously, the college scorecard data has a ton of attributes in it, far too many to list. So initially, I subset those attributes into the ones that I'm pretty sure I'm going to use across my analysis, or the more important variables that I want to use. And the usual suspects include the number of undergraduate students, maybe the average SAT scores, things like the type of school, public or private, we talked about that, admissions rates, the percentage of students that take out Pell Grants, or the percentage of students that take out federal loans. Those are the usual attributes that we use from the college scorecard. Now, even though I've narrowed down the number of attributes, I still have a bunch, right? And the overall curse of dimensionality is that the analyses get much harder and computationally complex when there's a lot more variables involved. One of the things that I can do to control that, or to make analyses a little bit easier, is to reduce the overall number of dimensions in the table that I'm working with. So instead of 10 dimensions or 10 attributes, I can narrow that down to 2 attributes. And when I apply dimensionality reduction, an interesting part of this is attempting to retain as much information as humanly possible within the reduced number of dimensions or principal components that you had in the original data. So if you have the original data that's 10 attributes, 10 dimensions, you have 100% of the information contained therein. But through the process of reducing the number of dimensions, you in effect lose some of that information without getting into too much of the theory, but you do lose some of that information when you reduce the number of attributes through principal component analysis. But the idea is to try and retain as much information as you possibly can. Okay, so the way to do this in R is very similar to, reading in the data, subsetting the attributes like I've done here. I have this little line right here, VTC, variables to convert. This just converts back to numeric. That's what this line does right here. You've seen that before. And anywhere there's an NA value, I make sure there's a 0 instead, because most of these analyses absolutely hate NAs. So you just replace them with zeros. Then I can use 2 libraries or packages. One's called Facto Minor, and the other one is called Facto Extra, to use a whole bunch of functions related to PCA, factor analysis, correspondence analysis, and so much more. One of the reasons why I might want to use PCA is because clustering doesn't deal well with a ton of variables. In fact, clustering is better if you can reduce the number of variables to 2, an x and a y axis. So the plotting is a little bit easier there. The function that I'm going to use from the Facto Minor package is simply PCA, all caps, and I'm only going to pass the numeric variables to this function. So I've actually subsetted the data to data frame to only the numeric attributes. And I can show you that here, data 2, right? You just open up data 2. In order, the counting starts at 1, so for column 1. And let's look at column 6, there's numeric, 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 all the way over to this final. Now it looks numeric, but guess what? These are simply numeric substitutions for categories. So these are actually categorical variables. The only true numeric variables I have here start at the admissions rate, or column 8 through column 15. So I need to make a little change. We're going to do 8 through 15 instead. Scale.unit tells PCA that these variables or attributes need to be scaled or standardized during the processing of this data. And NCP is the number of principal components that you want to look at or save by the end of this. So I take all that and I store this in a new object called PCA.results. This object will store all the results of this processing here, this algorithm.